In the 19th century, John Dalton, an English chemist, proposed a theory that changed our understanding of the universe. Dalton's atomic theory, published in 1808, posited that all matter was composed of tiny, indivisible particles called atoms. This marked a significant departure from the prevailing wisdom, which viewed matter as continuous and infinitely divisible. Dalton's theory had profound implications, suggesting that chemical reactions could be understood as the rearrangement of atoms. His work laid the foundation for modern chemistry and revolutionized our understanding of the material world. Dalton's atomic theory, while groundbreaking, was not without its limitations. He believed that atoms were indivisible and that all atoms of a given element were identical. However, subsequent discoveries revealed a more complex picture of the atom. Nevertheless, Dalton's contributions were monumental, igniting a scientific revolution. As the 19th century ended, scientists began to probe the atom with increasing sophistication. Technological advancements, such as the cathode ray tube, allowed researchers to peer into the subatomic realm. In 1897, J.J. Thomson, an English physicist, made a groundbreaking discovery while studying cathode rays. He observed that these rays were deflected by electric and magnetic fields, suggesting they were composed of negatively charged particles. Thomson's discovery of the electron threw a wrench into Dalton's atomic theory. Atoms were clearly not indivisible as Dalton had proposed. To accommodate electrons, Thomson proposed the plum pudding model, envisioning the atom as a positively charged sphere with negatively charged electrons embedded within it. The plum pudding model, while an improvement, was still incomplete. It could not explain certain experimental results, particularly those involving radiation. The stage was set for a new revolution in atomic theory, led by Ernest Rutherford. In the early 20th century, Ernest Rutherford, a former student of J.J. Thomson, devised an ingenious experiment to probe the atom's structure. Rutherford's gold foil experiment involved firing a beam of alpha particles at a thin sheet of gold foil. Based on the plum pudding model, Rutherford expected the alpha particles to pass through with minimal deflection. To his astonishment, some alpha particles were deflected at large angles, and some even bounced back. This unexpected result contradicted the plum pudding model. Rutherford realized that the atom's positive charge, and most of its mass, must be concentrated in a small, dense region at the center. He proposed the nuclear model, replacing the plum pudding model. According to the nuclear model, the atom consists of a tiny, positively charged nucleus at its center, with electrons orbiting at a distance. This model, with further refinements, forms the basis of our modern understanding of the atom. Rutherford's experiment revolutionized atomic theory. Rutherford's nuclear model provided a framework for understanding the atom's structure, but it left some questions unanswered. Further research revealed that the nucleus was composed of protons and neutrons. Protons, discovered by Rutherford in 1917, are positively charged particles. The number of protons in an atom's nucleus determines the element. Neutrons, discovered by James Chadwick in 1932, are electrically neutral particles. Together, protons and neutrons, known as nucleons, account for almost all of an atom's mass. Electrons, discovered by J.J. Thomson, are much smaller and occupy the space surrounding the nucleus. They are held in orbit by the electromagnetic force, preventing them from flying off into space. The arrangement of electrons determines an atom's chemical properties. For many years, scientists believed that all atoms of a given element were identical. However, the discovery of isotopes challenged this view. Isotopes are atoms of the same element with the same atomic number but different mass numbers. This means they have the same number of protons but different numbers of neutrons. Frederick Soddy proposed the existence of isotopes in 1913 based on his studies of radioactive decay. Isotopes share the same chemical properties but can have slightly different physical properties due to their different masses. For example, heavier isotopes tend to react slightly slower than lighter isotopes. Isotopes have numerous applications in fields like medicine, archaeology, and geology. Atoms are electrically neutral, with equal numbers of protons and electrons. However, atoms can gain or lose electrons, resulting in charged particles called ions. Ions play a crucial role in many chemical and biological processes. When an atom loses electrons, it becomes a positively charged ion, or cation. Conversely, when an atom gains electrons, it becomes a negatively charged ion, or anion. The formation of ions is driven by the tendency of atoms to achieve a stable electron configuration. The electrostatic attraction between oppositely charged ions forms the basis of ionic bonds, which hold together many salts and minerals. Ions are essential in everything from conductivity to nerve impulses. Atoms are incredibly small, and their masses are equally minuscule. To express the mass of atoms and subatomic particles, scientists use the atomic mass unit, or AMU. One AMU is defined as 1/12 the mass of a carbon-12 atom. The mass of a proton and a neutron is approximately 1 AMU. Electrons are much lighter, with a mass of approximately 0.00055 atomic mass units. Because electrons are so much lighter, their contribution to the overall mass of an atom is often negligible. The mass number of an atom, the sum of its protons and neutrons, is a good approximation of its atomic mass in AMU. The atomic mass of an element listed on the periodic table is a weighted average of the masses of all its naturally occurring isotopes. For example, chlorine's average atomic mass is calculated based on the relative abundances of its isotopes. The discovery of the atom and its particles revolutionized our understanding of the elements. Elements, the fundamental building blocks of matter, are defined based on their atomic structure. Each element has a unique atomic number, corresponding to the number of protons in its nucleus. This led to the development of the periodic table, arranged by Dmitri Mendeleev in 1869. The periodic table groups elements with similar properties together. Elements are arranged in order of increasing atomic number, with similar properties placed in the same vertical column or group. The periodic table reveals trends in the properties of elements, such as atomic radius, ionization energy, and electronegativity. It is an indispensable tool for predicting the properties of elements and understanding the natural world. The understanding of atoms has had a profound impact on countless aspects of our lives. From life-saving medical treatments to clean energy generation, atomic science has revolutionized numerous fields. In medicine, radioactive isotopes are used in diagnostic imaging and cancer treatment. Nuclear power plants harness the energy from nuclear fission to generate electricity. Nuclear energy provides a significant portion of the world's electricity and offers a low-carbon alternative to fossil fuels. However, nuclear power also poses risks, such as potential accidents and nuclear waste disposal challenges. In materials science, manipulating atoms at the nanoscale has led to new materials with enhanced properties. The study of atoms continues to drive innovation and shape the future of science and technology. From ancient Greek philosophers to modern-day scientists, the atom has captivated the human imagination for centuries. Its study has unlocked profound insights into the nature of matter and the workings of the universe. The atom, once thought to be the smallest indivisible particle, has revealed itself to be a complex microcosm. The journey through the atom's history and structure is a testament to human curiosity and the pursuit of knowledge. Each discovery, from Dalton's atomic theory to Rutherford's nuclear model, has built upon the work of those before. As we delve deeper into the subatomic realm, we continue to be amazed by the atom's elegance and complexity. The study of the atom is far from over, with scientists exploring fundamental forces and searching for new particles. The atom, once a philosophical concept, has become a gateway to a vast and intricate world, waiting to be explored.